we're on. All right, so electrochemistry. Now I'm going to start from the start, eh? Right, if I've got a beaker here, well, it's not a very good beaker though, is it? Right, let me do the beaker again, because that's not a very good beaker. Right, let me do the beaker. Oh, look at that, that's much better beaker. Oops. There's one beaker, and inside the beaker, I'm going to put a strip of zinc. Okay, so there's some zinc in the beaker. Okay, so this is zinc. Zinc metal. And in the beaker, I'm going to fill the beaker up with something like, I don't know, zinc chloride. Okay, so there's zinc chloride. And obviously, as you all know, zinc chloride is Zn 2+ ions, aqueous, and chloride ions. But I don't really care about the chloride ions. Now, if you could zoom in very, very closely to the edge here, you would actually have an equilibrium between the zinc and the zinc ions in solution. And the equilibrium would look like this. Zn metal, it would go into solution to form Zn2+, aqueous, and 2 electrons. All right, so that's what's happening. Some zinc, oh, Mosa's here at last. All right. Hello, Mosa, welcome. 10 past 7. Well done, dear. Right, so do we all understand there's going to be an equilibrium? Now, I've learned today, or I've learned quite recently, if you want to ask a question, either put your hand up or tap on, yeah, very good, yeah, you're having a problem there. Tap on one of the emojis. Look, I'm going to tap on there. You see that? Isn't that cool? Yeah. So if you're okay with things, do that. If you're not okay with what I'm talking about, do that. Okay? And if you have a question, like, I don't understand that, either that one or that one. Does that make sense, everyone? Are we all good? It makes quicker. Oh, yeah. Well, oh, look at that. You're using it already. Well done. Okay. So, all right, Mosa. Not you, dear. You're not allowed to yet. So far, so good. We're all okay. All right, good. Now, let's pretend that some ions have gone to zinc plus. So, believe it or not, let's pretend a couple of ions have gone in from the zinc metal to the solution. That means the solution will be a little bit positive because metal ions have gone into the solution. And that means some of the electrons will have been left on the piece of zinc. Oh, look at there they are. Isn't that amazing? Some of the electrons are on the zinc, so the zinc will be a little bit negative. Now, if that's the case, between the piece of metal and the solution, we will have what we call a potential difference. There's a difference in potential, all right? Because of that, we get sort of different charges or whatever. All right, so far so good, everyone? Thumbs up again if you're good. Is this too... Moses, okay. Are we all good so far? By the way, am I going too slow? Is this about the right place? Well, I'm going to have a sip of tea. Right pace, too slow? All right, Laurel thinks it's okay. Oh, that's nice tea. Right, a bit hot. Right, so there we go. We have a potential difference. Now, we can't do anything with this. Okay, we cannot do anything. Okay, I can't get this out. I can't do anything with this potential difference. It's there because zinc does its thing and the zinc solution does its thing. There's nothing I can do with it. All right. So, but there is one there. There's a potential difference there, but I can't do anything with it. Okay. So over on the right here, I'm going to draw another beaker. Okay. So there's one there and there. And into this beaker, I'm going to put a different metal. There. Oh, I don't know what that was. Do you want to? No, I don't. Oh, the computer's confusing me. All right, no, I don't want to do that. Right, and then I'm going to fill this up with another solution. This one's a bit neater, isn't it? I'm getting the hang of this thing. All right, now this metal, for argument's sake, is copper. Okay, and I'm going to put the copper in copper sulfate solution, which is beautiful blue, as you know. Okay, so let me do it in blue then. All right, so we have Cu2 plus and aqueous and Cu2 plus aqueous. Now, again, we're going to get an equilibrium set up between, what colour? I'll use that colour, between the metal and the solution. And the equilibrium will look something like this. Cu, whoop, no it won't. It will be Cu solid. Cu solid is going to be in equilibrium with Cu2 plus aqueous plus 2 electrons. All right. Now, and this is where it becomes kind of interesting. If zinc, let's pretend zinc put 2 ions into solution from the metal, will copper put more in or less in? Very simple question. Will it put more copper ions in or less copper ions than the zinc? Some things you've got to type in the chat because you can't answer that with an emoji, can you? So, anyone know? What do you think with copper? No one's going to say a word. More. Why? Why more, Basadi? I can see it's a guess because of the question mark. Which, yeah, Pencil was out off somewhere else. More. Why more, Laurel? Why would copper put more ions into the solution? You don't know. All right. Now, all right, I'll give you kind of the answer. Which one more readily loses electrons, Rose? Or maybe I'm saying it the wrong way around. I don't think so. Copper? Is copper more reactive than zinc? No, it's not. So which one is more reactive? Wait, what tin? What are you tin for? Zinc, dear, zinc. No. All right, let's start again. All right, zinc is more reactive. We know that, don't we? I hope we know that. More reactive than copper. That is easy. All right, yes. Nice one, Rose. Well saved. So zinc is more reactive than copper, and therefore zinc will form positive ions. Petzl, doesn't zinc have the likes of a remaining as an ion because it's more reactive? Yes, I think that's right, Petzl. Zinc will form positive ions more readily. Now, we actually say this because zinc is more reactive. It forms the positive ions more readily. We say, and this is in the syllabus, it has a greater tendency to form the positive ion. Are we all good with that? Is everyone good with that? Don't forget the thumbs up. Excellent. All right, so if zinc put 2 ions in, this is obviously just illustrative, but if zinc puts 2 ions in, copper will put how many ions in? More or less than zinc? Let's try again, shall we? Well done, Laurel. Thank you very much. It's going to be less. So let's pretend the copper only puts 1 in. Obviously, this is just for illustrative things only, isn't it? So there is the one that copper put in. So if copper only puts 1 electron in, Laurel and the rest of you, how many electrons are left on the piece of copper? How many electrons were... Wow, Laurel! How many electrons will be left on the copper? If Cu2 plus goes in, how many electrons must be left on the copper? 2, yes. Are you just counting now? All right, 2 electrons. Let's start again. Yes, Rose. Have a look at the zinc. How many ions went in from the zinc? 2 ions went in from the zinc. How many electrons have I shown on the piece of zinc? 4. I've shown 4. Okay. Why is there 4? Well, for each ion that goes in, 2 electrons are left behind. Can you see that? Oh gosh, someone's doing something outside. Can we say, well, thanks, Basadi. Now, for each copper ion, how many electrons are left? 2 electrons again, okay? But in the case of zinc, we're going to have 4 electrons on the piece of metal. But in the case of copper, we only have 2 electrons on the piece of metal. Is that clear, everyone? Because copper is less likely to form. Well done. So we're good there. So what do we have here? We have, I don't know if you can see, this is right at the edge of the page. Oh, that looks pretty ugly. We have, this is going to be, oopsie daisy, that's not right at all. I have no idea what the noises are outside. This is going to be a little bit negative, and this is going to be a little bit positive. And what do we have? We have another potential difference. There's another. Oh, what's wrong, dear? Basada, you've got to type something in. There's another potential difference. Nothing written. Nothing's written. What? Nothing's written. Is that a biblical quote, Peter? What's going on? All right. Basadi, what's wrong, dear? I saw an emoji. Means you don't understand something. You're okay. All right. So potential difference. Okay. Now again, what can I do with this? I can't do anything. Can't do anything with this. I can't do anything with either of them. Okay. But so Zn2 plus solution is more positive, but the Zn enrichment is yes, dear. That is exactly right, Rose. All right, it's not a biblical quote, no. Well done. So, what am I going to do to these two things then? What's obvious? What am I obviously going to do to them? Anyone know? Musa should answer this one and stop quoting the Bible. What am I going to do with these two cells, or half cells? Anyone? No? Yeah, join them up. Well done, Peter. I'm going to join them together with a piece of wire. Now, here I go. Look at this. There goes the wire. I'm going to put a voltmeter there, and I'm going to do that. Okay. Now, even though the zinc metal is negative and the copper metal is also negative, they're both negative, yet one is more negative than the other. And therefore, which way will electrons flow? From which side to which side? Yeah, from the zinc to the copper. Exactly. Well done, everyone. So electrons hate each other, don't they? And look at them. There's lots of electrons here. They'll push each other apart more than the copper electrons will push each other apart. So what's going to happen is electrons are going to flow from this way to this way. Okay? And that means the zinc metal we call the negative, because it's the one that supplies electrons. This is the negative electrode. And because it supplies the electrons, it pushes them to the copper. And the copper is the positive electrode. Are we all good so far? Excellent, well done. Only 2 people said it, so well done, Musa. All right, now, it's crazy, but this is the fact of life, I'm afraid. How long will current flow for? The current will flow for maybe a millisecond. Okay, what will happen is the electrons will flow over until the electrons are equalized, and that will be about a millisecond. It won't be long. All right, we'll get a spike in current, and then it will stop. Okay, and the reason it stops is, well, because everything's been equalized, and there's no way out for things to happen. So to create a circuit, we have to add something else. Okay, we have to have, that's right, Rose, a salt bridge. And the salt bridge will do something like that. Now, the salt bridge in its simple form is salt like potassium nitrate, okay, dissolved in water, and it's made of filter paper. Okay, we make it out of filter paper. Now, what happens is electrons keep leaving the zinc, and because electrons keep leaving the zinc, negative ions will come and join this solution. So nitrate ions come in here. Okay, electrons keep joining the copper side, so that gets more negative, and because of that, positive ions join here from the salt bridge. And it keeps the electrons flowing. It keeps the two solutions different, as it were. Okay, it keeps the potential difference between the two. Okay. If someone asks you why do we need the salt bridge, the best one. All right, what I will in a minute. There's something from Petzl in a minute. We say it keeps the it completes the circuit. Completes the circuit. Okay, right. Is this any? Yeah, we can use loads of compounds. Potassium nitrate is probably the most common. All right, but there's loads. Potassium chloride. Potassium is a common one. Yeah, obviously I can't think of any at the moment, but you can use loads of things. All right, potassium sulfate, sodium sulfate you can use. You can use lots. Now, Wilder wants me to explain it again. Right, before I go on, salt bridge chemistry. Salt bridge chemistry is complex, number one, and it is not on your syllabus. It's not on the syllabus, so you don't have to worry about it. But I'll explain it anyway. Can you see, Wada, that on the left, the zinc solution is losing electrons? The left-hand side of the thing is losing electrons. Yes? So as it loses electrons, it becomes more and more positive. The whole left-hand side becomes more and more positive. And therefore, the salt bridge will give me negative things, so it doesn't get too positive. So out of the salt bridge, we'll get nitrate ions because they're negative. On the other side, the copper side, it keeps gaining electrons because they're pushed onto it. Now, if it gains too many electrons, no more electrons will pass because the electrons will be repelled. So what happens is the salt bridge supplies positive ions to negate the effect of all the electrons on the piece of metal. Does that make sense, dear? It's complicated. Wonder, it's not easy, this, eh? Very complicated. So, roughly speaking, do we understand everything there? Hold on, Rose. Does the salt bridge need to be replaced? Yeah, exactly. It does. It dries out, dear, more than anything. Yeah, you have to keep it wet because you want ions to flow through the salt bridge. Okay, so nitrate ions come off of one end and potassium ions come off the other end. Yeah, but we have to, number one, we have to keep it wet. And number two, we have to keep it saturated. But again, salt bridge chemistry isn't on your course. Interestingly, the easiest salt bridge is a piece of filter paper. But these days, what they tend to use is a tube, a glass tube. And inside the glass tube is a paste of potassium nitrate, which is loads of potassium nitrate and some water. And it's like a toothpaste in there. And it kind of goes across. If I can find one, let me see. I'm going to go on the internet now, see if I can find a salt bridge picture. I bet it won't give me anything interesting. Yeah, it's nothing interesting so far. Oh, there's a good one. Yeah, let's see if I can cut that out for you. It's exactly the one we want, actually, believe it or not. Right, stick that over there. And do that. Okay, copy that. And paste it there. There. Can you see that? It's not a very good picture, but it's an okay picture. Can you see that? So on the left is the copper, on the right probably zinc, and can you see the salt bridge in the middle? It's like a piece of glass tubing. All right, there you go. It's a nice salt bridge, that one. It's a nice picture. All right, let's get rid of that. Okay, so we're good. So everyone's good so far. All right, which is good. Well done, Rose. Now, what's the voltage here? Well, the voltage is going to be 1.1. Oh, that's not good. Sorry about that. My pen is weird. It's going to be 1.1 volts. Okay. If I hook these two up together, it's a very common voltage, that 1.1. Okay. So, but we don't know. We don't really know what's happening here. All we know is the potential difference between the left-hand side and the right-hand side is 1.1 volts. Okay, now, those of you that do physics will know this. If you don't do physics, you'll have to listen. Voltmeters only work if they're put into the circuit the correct way round, okay? And they'll only work if the positive side of the voltmeter is connected to the positive electrode, okay? And the negative side of the voltmeter is the negative electrode. So what I can tell from this 1.1 volts is the potential difference between these two half cells is the potential difference of these two half cells. There's a lot of spraying going on. I think it's the pressure cooker. I think my wife is doing something with the pressure cooker, but she's making a hell of a racket, I'll tell you. So the potential difference is 1.1 volts, and the negative electrode is the zinc. Okay? All right, are we good there so far? That's what we can tell so far. All right. Now, but I don't know really what's going on here. So what we have to do is, because we can't measure the electrode potential of this, and we can't measure the electrode potential of the copper, we cannot do it. We will never know what they are. Okay. So what we have to do is a cheat. We have to cheat a little bit and say, well, I don't know what they are, but what I'm going to do is I'm going to get a standard electrode potential, and I'm going to measure everything relative to that. Okay. Now, do we do that in everyday life? Well, we do that in everyday life, because you have no idea. You pick a stone up from outside. Okay. There's a stone from outside. Okay. And I ask you, what's the mass of this? Okay, not one of you could tell me the mass of that. Okay, you can't tell me the mass of that stone. So what we do is we make up this thing, and there's a cylinder that we've made up. Humans have made it up. It's made of palladium and something else, rhodium, I think, but I might be wrong. Okay, it's kept in Paris. And we say it has a mass of 1 kilogram exactly. Okay, but we don't know what the mass is. It's only a kilogram because we say it's the kilogram. And now what we do is we measure the mass of this stone and compare it to the kilogram. So everything must be compared to some sort of base unit. Does that make sense? We don't know the electrode potential of the copper. We don't know the electrode potential of the zinc. So we have to do it. We have to have some sort of standard. Okay. And the standard for this is, does anyone want to type it down before I manage to write it? The standard hydrogen electrode, also known as the She. I don't know what H2 means, Musa, but the She. Okay, the standard hydrogen electrode. Now, I'm going to draw it roughly. You've got to be able to draw this, by the way. Right, oops, that doesn't look good, does it? I'm doing this from memory, so you've got to manage to do it. So on the left-hand side, we've got that. This guy's in a beaker. And it's filled up here. Now, in here, we pump in hydrogen gas. Now, the temperature is vital, 298 K. The pressure is vital, is 1 atmosphere. All right. And there you go. We pump hydrogen in there and there. All right. Now, let's do the other bits and pieces with a different color. That's blue is a good color. Now, at the bottom here, we have a piece of platinum. Oh, that's ugly, isn't it? There you go. There's my voltmeter. Okay, and I'm going to connect it over here. I'm going to connect it to my zinc. And there's my zinc. I'm going to put the zinc. Well, that's not a very good picture, is it? But it will have to do for today. There's my zinc. All right. And the zinc. And it's in zinc 2+ ions here. Okay. Now, this solution on the left is H+ ions, aqueous, and the concentration of this must be 1 mole per decimeter cubed to make it standard, and the concentration of this zinc must be 1 mole per decimeter cubed as well. That's the standard concentration. Standard pressure is 1 atmosphere, 298 K. Standard concentration is 1 molar, and 1 molar. Okay, I think that's everything. Oh, and there's a salt bridge, isn't there? And we've got to have a salt bridge between them. All right, to keep the thing going. Now, this bit of platinum over here, Okay, it's very, very high surface area. Okay, and the hydrogen, let me do the surface. This is all air in here. There's the surface, and bubbles pop out here from the sides. So hydrogen goes in there and it bubbles out. But this platinum, interestingly, has a very, very, very high surface area. So this has a high surface area of platinum. Okay, so is the surface going to be rough of that platinum, or is it going to be smooth? What do you think? Lovely. Is the surface area of the platinum going to be rough or smooth? Do you think? It's going to be very rough, yeah? And the reason it's rough is we want it rough because it's going to capture hydrogen bubbles onto it, yeah? Now, Laurel, see if you can get this, dear. If the platinum is rough, all right, that we're using, is it going to reflect light nicely or not nicely at all? Anyone can answer this. Is it going to reflect light? It's not going to do it nicely, is it? So if I had a piece of platinum in front of me and light fell on it, but it doesn't reflect light well, what color will the platinum appear to be? What color will the platinum be? Well, actually, yeah, it's actually, oh, Tamani, well done, nice one. Yeah, it's going to be black. Okay, well done. Because it has such a high surface area, all right, it doesn't reflect light. And so, therefore, this platinum is known as, it's called platinum black. Okay, we call it platinum black. Now, the black just means it has such a high surface area that it doesn't reflect light. And the reason we want it to have a high surface area is because it captures the bubbles. The bubbles stick to it. All right. So, I don't understand how the roughness gives it a large surface area. Darling, did you do biology in IG? Yes. What about the villi in your lungs? Is it villi or is that in the stomach? But mucrovilli. Yeah, are your intestines? Yeah, I know, Rose. It's micro. Are your intestines smooth, Basadi, or are they rough? Sarcasm won't get you anywhere, Mosa. We all know you were 10 minutes late. Yeah, rough because it's to increase the surface area, isn't it? What about your towel, Basadi? Do we dry ourselves with a towel that is smooth? No, everything that's rough has a high surface area, doesn't it? The rough bits give it a high surface area. Does that make sense, Basadi? Are we good, Basadi? Yeah, oh, you get that. All right, good. So soft towels only. Yes, very good. Mosa's off on one, as they say. Right, now, where are we? The equilibrium here is going to be H2 gas, and it's going to form my 2H plus aqueous plus 2 electrons. And the one over this side is going to be the one we did earlier. Zinc goes to Zn2 plus 2 electrons. All right. Now I hook these up. So why don't we use PD powder? Here's a reason it has to be a solid clump. Well, it's got to be connected, Rose, here, doesn't it? Yeah, there's got to be something that dips in the liquid, and a powder would be a pain, wouldn't it? Wouldn't it keep flowing off somewhere? Yeah. So yeah, we use a piece of platinum. It's just roughed up platinum, and roughed up platinum looks black. Okay, the more you rough it up, the blacker it gets. All right. So anyway, so we hook this all up, and I find on my voltmeter I'm going to get 0.76 volts. Okay. Now the way I hook this up, I find that, believe it or not, where's my color? This red color is good. I find out that the positive of my voltmeter is connected to the hydrogen side, and the negative of the voltmeter is connected to the zinc side. So that must mean electrons flow from the zinc to the hydrogen. Yes, that's what happens here. So the zinc is therefore the negative electrodes, and the hydrogen must therefore be the positive.